So let's take a look at this problem in universe gravitation. Suppose I have an object which are launched directly upwards, vertically upwards from the surface of the Earth with a certain initial speed. I want to know how high this object can reach before it comes to a stop and come back down. The initial speed is the so-called escape velocity, and that's the minimum speed it takes to escape the gravitational pull of the Earth. The first part of the problem asks us to find what that escape velocity is. Now, that's a standard problem. Many of you have seen how we do that, or maybe figured out how to do that yourself. But as a review, we're going to do that first. And then we're going to take a look at what happens if the initial speed is half of that escape speed. Then, of course, it cannot quite reach infinity. We can see how high it can go. Okay, so let's look at the first part. The first part of this problem, find escape velocity. Okay, the key idea here is that if you ignore air friction, then as the object is launched, the total energy of the object, that is the kinetic plus the gravitational potential energy, remains the same, because the only force acting on the object is the universal gravitational force of the Earth. And that, of course, is a conservative force, and there's a potential energy associated with that. So the total energy, kinetic plus potential, is a constant for that object in flight. So let's use that to figure out the universal, the escape velocity. The initial energy, E initial, equals to the final energy, E final, okay? And here, the initial state is when it's launched from the surface of the Earth, and the final state is when it escapes all the way to infinity, right? So I have K initial kinetic energy, plus U initial equals K final, plus U final, right? Now the K initial is 1/2 mv squared. 1/2 mv squared. V is the initial velocity of the launch. Okay, U initial is when is the potential energy of the object right on the surface of the Earth. Now the potential energy of an object in the Earth's gravitational field equals negative big G times mass of the Earth times mass of the object divided by the radius divided by the distance between the object and the center of the Earth, and then plus a constant. Now we can say that constant equal to 0, then I get a expression of negative G mass of the Earth, mass of the object divided by the radius of the Earth. I'm going to denote the radius of the Earth as capital R, okay? And so that is the initial potential energy. The final potential energy, 1/2 mv final squared, and then minus G mass of the Earth, mass of the object over R final, okay? Now, in our case, we're looking for the minimum speed it takes for the object to go all the way to infinity. So we know that V initial is V escape, right? That's what we're looking for, V escape. And we also know that R final equals infinity. Okay, R final equals infinity because it can go all the way to infinity. And V final equals 0 because we're looking for the minimum initial speed. So by the time it reaches infinity, there is no kinetic energy left. Okay, so the right-hand side equals 0. Both terms are right-hand side equals 0. So I have this equal to 0. And then I can find V initial, V escape now. V escape equals the square root of 2G times the mass of the Earth over the radius of the Earth. Okay, now we can find a numerical value of that. Of course, you can plug the value of big G, the value of the mass of the Earth, the radius of the Earth, and so on. But there's an easier way to find the numerical value. There's a small trick that we can use, and that is if you stand on the surface of the Earth, your weight is your mass times the acceleration gravity on the surface of the Earth, which everybody knows is 9.8 meters per second squared, right? On the other hand, this force really is just a gravitational attraction between you and the Earth. And so that this force, we know the magnitude equals to G times the mass of the Earth times your mass over the radius of the Earth squared. Okay, if you cross up both sides, small mass, your mass on both sides, then I know that big G times the mass of the Earth is just the acceleration gravity times the radius of the Earth squared. Okay, and that allows us to find the escape in a simpler expression. It is then equal to square root of, okay, G times M equals small g times r squared, and there's a 2 here. And there's r squared divided by r, so what you have is 2gr. This is obviously a simpler expression. G is the acceleration gravity, r is the radius of the Earth. So you can now find a numerical value. All you have to do is plug in the value of small g and the radius of the Earth. 2 times 9.8, I'm using SI units, meters and seconds, and so on. So R is 6,400 kilometers, about 4,000 miles, okay? 6,400 kilometers, convert kilometers to meters, that is 6.4 times 10 to the 6 in meters, okay? So the answer will be given in meters per second. And that is 11,700 meters per second, or 11.2 kilometers per second. Okay, that's a lot. That's very, very fast. Kilometers per second, not per hour. That is the escape velocity. Okay, so by now everybody should be quite familiar with this calculation. So that's part 1 of the problem. Now, part 2, suppose the initial launch speed is half of that speed. Then how high can it go if I launch it vertically up? So you go from initial to the final state, okay, vertically upward with half of the escape velocity, and you want to know how high it can go. Okay, so let's see how we can do that. So this time I have V initial equals half of V escape. Okay, now if you have V escape, then the initial kinetic energy, this term, and the initial potential energy, that term, they would have the same magnitude, right? So the left hand side is 0, right hand is also 0. But if you have half of the escape velocity as V initial, then if you square that V initial, you get a quarter of V escape speed squared. And that means the magnitude of the initial kinetic energy this time is only a quarter of the magnitude of the initial potential energy. Okay, this will be useful in our simplification. So now I have now I have 1/2 m V initial squared, and that equals to, as you know, 1/2 m V escape hold on, there's a delay, V escape over 2 squared, and that is again a quarter of the initial kinetic energy if it's moving at escape velocity. Okay, so 1/4 of 1/2 m V escape squared, right? And that equals to 1/4 of G, mass of the Earth, mass of the object, over R. Okay, how do we get the last identity? because again, if you have v initial as the escape velocity, then these two terms have the same magnitude. That's why both sides are equal to 0. Okay, so that's a simplification that we'll be using later. So now let us again use the conservation of energy. So set again E initial equal to E final. Okay, so this time E initial is again K initial plus V initial. K initial is right here. This is K initial. So this is K initial, right? So I'm going to write 1/2 m initial squared, and then minus the same expression for the potential energy initial value. I'm going to set it to final energy, K final plus U final, but K final equals 0 because by the time we reach the top of the motion, you're no longer going up, so you have stopped. So there's no kinetic energy at the final point. The final potential energy is negative G mm over the final distance between the center of the Earth and that object. And if you look at this here, the center of the Earth is right here. Okay, here's the radius r of the Earth. But you are at the top of the pass. The distance between that object and the center of the Earth this time is the radius r of the Earth plus h maximum. H maximum is the maximum altitude. So I can write here is r plus h maximum. Okay. Okay, of course, I'm looking for h maximum. This expression can be easily simplified if I use what we saw earlier. And that's this equals that. So I can rewrite the first term of the left-hand side as a quarter of the magnitude of the second term. So I can now write 1/4 of GMM over R minus GMM over R equals to negative GMM over R plus H maximum. You see how simple this becomes, because you can cross up GMM over R. There's such a term in everywhere. And then you can just look for H maximum as a function of R. You can easily do that. And the algebra is simple. That I'll just leave it alone, leave it for you to complete that, and you will find that H maximum it simply equals to 1/3 of radius of the Earth. Okay. And since R again equals 6,400 kilometers, so you get about 2,100 kilometers. So that is the answer to part 2 of the problem. If you launch this object at initial speed, which is a half of the original escape velocity, it cannot go all the way to infinity. It can, but it still will reach 2,100 kilometers above the surface of the Earth. Okay, so all we used here was the conservation of energy. Right? Now, the third part of the problem is more interesting. Because the third part of the problem, you're not launching the object vertically upwards. Okay, you're launching at an angle of 60 degrees above the horizontal. Now, if the angle is 90 degrees above horizontal, that's a vertical launch, which we saw earlier. So if you launch at 60 degrees above the horizontal, it will follow a path like we saw, like we see in this diagram here. Is that a parabola, by the way? It looks like a parabola. Is that a parabola? No, it's not a parabola. Okay, it is a parabola as a good approximation if H maximum is far less than the radius of the Earth. So you're looking at, launching a projectile near the surface of the Earth. We know, of course, from all the way back in chapter 2, it is chapter 4, it is a parabola. But if we're looking at a large initial speed launch, then it has to go pretty far from the center of the Earth, meaning that the gravitational acceleration is no longer constant during the flight, and therefore it's not a problem. Okay, but we're not interested in the shape of this trajectory for this particular problem. Actually, we do know it should be part of an ellipse, right? Because you can think of this as an object moving around the center of the Earth. So it should be part of an ellipse, but that's not what we're talking about here. We're talking about a special point on that trajectory, that is when it's furthest away from the center of the Earth. Okay, we call it the final point. I want to know how far it is to the center of the Earth. That is the maximum altitude. Now we know, common sense tells us the maximum altitude in this case should be less than 2,100 kilometers, because we're not launching it vertically upwards. We're launching it at an angle, right? So common sense tells us that the answer should be a little bit less than that. But how much less is that? And how does that depend on initial angle theta? Well, that's something we should investigate. Okay, so let's see how we can do that. All right, now, here's the thing. You have conservation of energy, okay? Because still, the only force acting on the object in flight is gravitational force, which is a conservative force. But the problem here is that conservation energy alone doesn't solve the problem for you. It does not. You need something else. Why do I say that? Because the conservation of energy relates initial and final total energy. You're looking for the final height H maximum, but there is another variable, and that is the final speed when it reaches the top. Now, in the past, we set this to be equal to 0, and V final equal to 0 because it's a vertical launch. But is V final also equal to 0 for this launch? No, it is not 0. Common sense tells us it's still flying, except it's flying for this particular moment, it's flying parallel to the surface of the Earth at the same point. Okay, it is flying forward, but it's not moving. It's not at rest. If it's at rest, what do you think happens next to this thing? If there's no initial speed and the Earth's gravity just pull it directly downwards, right? It's going to just descend vertically downwards to the surface of the Earth. So we'll end up at this point, right? Which makes no sense, right? It actually continues to fly, right? So what is V final? We know it's not equal to 0. So there's a second variable here, V final as one variable, H maximum as another variable. There are two variables here. We need two equations to solve them. One, of course, is the conservation of energy. What is the other one? What kind of conservation law can we use in addition to the conservation of energy? Now, we know there is conservation of energy, momentum, and angular momentum, right? These are the three conservation laws. You can forget about conservation of momentum. Why? Because for the object, the Earth's gravitational force is an external force. It constantly changes the momentum. Otherwise, the thing which is flying in a straight line, which we know is not the case. So you don't have conservation of linear momentum. You already used conservation of mechanical energy. What's left? The conservation of what? Angular momentum. What is the condition for that? For angular momentum, the condition is that the torque acting on the object is 0. Now, is that true? Okay. I want to know if the torque acting on this object is 0 or not. Well, what is the torque equal to? The torque acting by a force on a point mass is equal to R cross F. Okay, R cross F. Now, in this case, R is from the center of the Earth, point O, to that object. Okay, that's R, the position vector R of the object. But the force of gravity points from the object back to the center of the Earth, right? So R cross F You look at R cross F, that's the torque acting on this object. Okay, you find that this torque actually equals 0 because F is along the direction of R with a negative sign. So it's anti-parallel to R. So R cross F equals 0. This is not specific to gravitational force. It is anytime the force points directly from the object back to a certain fixed point, in this case, the center of the Earth, R cross F would be 0. So there is no torque acting on this object. Therefore, we have conservation of angular momentum. Okay, so that's the second conservation law we can use to solve this problem. Okay, so look at the first conservation law. I can write here that L initial equals L final. Okay. So now we can write down the two conservation law equations. And you see here the first one, the conservation of energy, as we just like before. Okay. This one is just like before, except that the final speed is no longer 0. And now we can look at the conservation of angular momentum. The angular momentum for a point particle of mass m moving with a velocity v is r cross mv. If you recall from chapter 11, r is the position vector of the point mass measured from a certain point, which in this case is center of the Earth. Now, when you go r cross mv, you find that I can rewrite this as mv perp times r. V perp is the component of velocity that's perpendicular to the vector r. So in this case, look at the initial value of the angular momentum. Here is the initial position, that's where it is. So R initial is from O to the initial point I with a value which is equal to the radius of the Earth. And if you draw a line perpendicular to that, and that will be the horizontal direction, and you break down this V initial into that direction. So we're looking at the horizontal component of the initial velocity. That is V initial times cosine theta. Theta is equal to 60 degrees. Okay, so L initial, the initial value of the angular momentum of the object is mr V initial cosine theta. Now, for the final position, which is top point, it is moving perpendicularly forward from the position vector r. Okay, so basically this vector and that vector, they're already perpendicular to each other at that point because it's moving. It can no longer be any higher. Therefore, it is not moving radially away. Okay, so for the final angular momentum, it's just m magnitude. It's just m times the final distance between the object and the center of the Earth, which is r plus h maximum, and then times v final. There's no cosine factor here anymore. Angle is already equals 90 degrees. Okay, so equate the initial and final angular momentum magnitude, we get the last equation. You combine the last equation with the first one, this one right here, and we have two equations, we have two unknowns. So in principle, we can go ahead and solve it. So what's left is the math problem, how you combine these two equations to solve them. There are a couple of things. One is, as you know, the 1/2 mv initial squared. This first term on the left-hand side of the conservation of energy equation is a quarter in magnitude compared with the second term of gmm over r. So that's one thing you plug in. The other thing is you can solve from the second equation to conservation of angular momentum. You can look for v final in terms of v initial, in terms of everything else, in terms of h maximum and everything else. So you basically solve for v final from the second equation and plug into the first one, the one for the conservation of energy, and utilize the fact, again, that the initial kinetic energy is a quarter in magnitude of the initial potential energy. And then you arrive at one single equation. This equation has h maximum as the only unknown. Now, to simplify this equation, we can set x as h maximum over r, is a new variable x. Okay, and then you will find x satisfies this equation right here. X satisfies this equation right here. This is the quadratic equation for X, and you can go ahead and solve that. Theta equals to 60 degrees, so cosine squared theta equals 1/2. So you finish all that, you find that X equals roughly 0.268 times the radius of the Earth, and that'll give you the H maximum in our new case of about 1,700 kilometers. And indeed, it is lower than the altitude reached from the first case when launched vertically upward, in which case is 2,100 kilometers. Okay, so the new physics here is that you have to use a combination of the conservation of energy and the conservation of angular momentum, which is true anytime this object is being influenced by a force which points from the object to the center of that, to a certain center, which in this case is the center of the Earth, with conservation of angular momentum in addition to the conservation of energy.